Okay, let's go to capacitors and dielectrics. A capacitor or condenser is a device that stores charge and electric energy. To this analysis, let's use a two-plate parallel capacitor. And let's use a battery and connect these two plates to a 6 volt battery. Of course, we have charge on these two plates. Later, we remove the battery and measure the voltage. It's found to be the same. What happens if we increase the voltage to these two plates? Well, the charges stored on these two plates increases too. So what do we have then? We have that the charge is proportional to the voltage. If I increase the voltage, I increase the charge. Correct? Now let's eliminate this symbol using a constant. So charge is equals to a constant times voltage. This constant depends on the capacitor, depends on some dimension. I have to find it later. Great. So from here, we can solve for C. C is called the capacitance, this constant. C is capacitance, right? And it's equals to charge divided by voltage. Right here we have some formulas from previous chapters that help us to work with the capacitors. Well, we have then the capacitance is equals to charge divided by voltage. This is a new quantity, and of course it has a unit. The unit is called farad. So 1 farad is equals to coulombs per volt. Right, 1 farad coulomb per volt. Okay, now let's go back to the analysis of this capacitor, and now let's add, let's say, some dimensions. Let's add the area, and let's add the distance. We have a distance between these two. Also remember we have electric field in this plate. This is the electric field. Now let's add these two quantities to the capacitance and see what happens. Let's do it. Great. In this case, we use this quantity, previous quantities, and then what do we have? Capacitance is equals to charge divided by volt. But where can we find charge with these quantities is related to the capacitor? Well, from this equation, it was found before. The electric field for a capacitor is equals to sigma divided by epsilon naught. Sigma is the charge surface density, and it's equals to charge divided by area, in this case times epsilon naught. Correct? Epsilon naught. Okay, perfect. Maybe this is the permittivity of free space. Great. And what about volts? Well, we can substitute this value right here. We solve for charge is equals to the electric field times area times epsilon naught divided by voltage. But voltage, we can use it from here. It's equals to AD. It's equals to the electric field times the distance between these two plates. And then this is found that the capacitance is equals to area epsilon naught divided by the distance. Okay, we have another formula for capacitance. Area epsilon naught divided by the separation between these two plates. Great. Now, let's go back to the case when we use dielectrics. Okay, let's see what happens when we use dielectrics. A dielectric is just an insulator or a non-conductor. Let's do it. Let's go then to dielectrics. Yes, and let's repeat. And let's use the same capacitor, right? This one. Let's erase these quantities right here. Imagine. So we have these two plates. We charge these two plates, right? And then I will remove the battery, and it's found to be the same voltage as before. And now let's place in this capacitor or two plates a dielectric and see what happens. When we place a dielectric right here, right, a dielectric inside This is dielectric. Well, the voltage decreases, right? The voltage decreases. The final voltage is less than the initial voltage. This is found from the experiment. For example, imagine that this is 6 volts, and for this particular dielectric, B final is equals to 4 volts. For example, let's increase this voltage, let's say to 9 volts. It's found that if we use the same dielectric, the same distance between these two plates, that the final voltage, case 1, case 2, the final voltage is equals to 6 volts. Correct? Now, we can see that in this case, voltage is equals to the initial voltage divided by 1.5. If we divide by 6 by 1.5, we get 4, and we divide 9 by 1.5, we get 6 volts. This is found from the experiment, correct? Means that this is the final voltage equals to the initial divided by a constant. This is called the dielectric constant, and the symbol is kappa, right? Kappa. Kappa. And this is the dielectric constant. That depends on the material, right? That depends on the material. So in this case, we can represent the voltage is equals to the final is equals to the initial divided by kappa, the dielectric constant. Correct? Perfect. Now let's see what happens. In this case, look, we remove the battery and we place the dielectric. Let's repeat the experiment, but without removing the battery, and let's see what happens. Let's do it. Imagine that we have this case one more time. This is 6 or 9 volt. And let's take 6 volt, and we keep the battery connected. In this case, now the battery is still connected right to the plate. Imagine. Again, this is 6 volt. And now we place a dielectric. Imagine it's the same dielectric. Okay, the same dielectric right here. Okay, perfect. This is dielectric. It's found that the charge increases. Correct. This is now the final charge. Positive charge, right? Negative charge. So in this case, the final charge is greater than the initial charge. The charge increases, the charge stored in the capacitor increases if we add a dielectric, right? Dielectric. The dielectric could be a plastic, could be wood, could be a paper, and so on. Okay, great. Now, let's see what happens because the voltage is the same. Look, the voltage is the same. We can divide this by voltage and by voltage right here. Because this is the same at the end, at the beginning, or we can place also in this way. But what is this charge divided by voltage? Well, it's the capacitance. So the final capacitance is greater than the initial capacitance. Initial capacitance. Now, we introduce the same concept as right here, right? The concept of the electric constant, and it's found also by the experiment that the final capacitance is equals to kappa times the initial capacitance. So the final capacitance is equals to kappa times the initial capacitance. Means what? We have these two plates connected to a battery, and we place the dielectric, the capacitance increases. The capacitance of this capacitor, because it stores more energy. More charge in this case is charge. Right? Perfect. Great. Now let's see when we use the formula of capacitance one more time. This one is capacitance because this is the initial, right? Without we found this one, remember, using this capacitor without without the dielectric. Now, when we have the dielectric, well, we use this one. So, in this case, the capacitance is equals to kappa, right? That's the symbol for kappa, times the initial capacitance. The initial capacitance is without the dielectric. It's equals to A epsilon naught over D. This is with dielectric, right? Without dielectric. Again, this is for a parallel plate capacitor, right? Perfect. Now we already defined, right, or work with the charge stored. Now, what should be the energy that is stored in this capacitor? Let's find the energy. Great. When we have a capacitor, right, imagine like this one. At the beginning, of course, this is not connected to the battery. Right? Okay, let me put it this way. We have this plate. Let's pay attention on this plate only. Okay, it is neutral, it's not charged. Let's plate this to the, connect this to the battery. So what happens? Let's do this in slow motion. At the beginning, we have a charge right here. Then another charge is coming. It's coming and it's placed right here. Another charge is coming, right? But the new charge is repelled by these two. So the battery is doing work. It's doing work on charging this plate, right? Imagine this is the third charge. Another charge is coming, but because they have the same polarity, positive and positive, they repel. But the battery is doing work to store the next one and so on, correct? So in this case, what should be the work done by the battery to charge these two plates? Well, let's go back to the formula that we found before, right? Potential difference is equals to work divided by the charge, which is the total charge right here, positive one, correct? And then how should it work? Remember, work is related to energy. Work is related to energy. Work, when we're dealing with potential energy, for example, work, remember, is equals to negative the change in the, let's say, electric potential energy, or negative change in the gravitational potential energy. We found it in the previous chapters, right? So we can use work or we can use energy in this analysis right here, right? So we have that then work equals to charge times the voltage. But look, the voltage, we found that is proportional to the charge. If we create the charge, the difference between these two, between these two plates, by the amount of charges, we increase the voltage, right? So at the beginning we have some volts, and zero. At the beginning was zero, and at the end we have the final voltage or volt, right? Perfect. And in this case, the voltage is increasing, is changing from 0 to 1 final, right? When that happens, we use the average voltage. The average voltage, and this is the average voltage. Remember, when we have this final change in voltage or potential difference, right, is equals to, let's say, final minus initial divided by, in this case, because we're dealing with the average. This is not the average, correct? What should be the average then? The average is gonna be V final plus V initial divided by 2. Instead of this one, we use the average, correct? Perfect. Now, what is the initial voltage? The initial voltage is 0, right? It's 0. So what should be the average? The average voltage. Again, we use the average voltage in this formula. This is equals to the final divided by 2, or the total at the end. Okay, perfect. And then instead of taking this work, we take this energy, right? So energy is equals to the total charge times the voltage divided by 2. Correct? So this is the energy stored in a capacitor equals to the total charge times the final voltage divided by 2. Also, we can add the capacitance in plug right here. What do we have? We have this equals to charge squared divided by 2c. And also, if we solve for the charge, what do we have? In this case, we have this v squared times capacitance divided by 2. Okay, perfect. Now let's go back to the energy, right? Let's go back to the energy one more time. Energy is equals to, let's start with the initial equation right here. Energy is equals to the charge voltage divided by 2. Correct. Now let's go back to these equations. And what do we have? Well, we found that the electric field is equals to sigma by sigma is charge over area epsilon naught. Correct. And also we have the voltage is equals to, well, we use this one, right? ED. Correct. Perfect. Let's substitute these values right here. What do we have? Well, then energy is equals to, let's solve for the charge. 1/2 times electric field, what else? Area epsilon naught times voltage. But what is voltage? Voltage right here, come on. Voltage is this one, okay. V is equals to ED, okay, great. So now V times ED. So what is this now? This is equals to 1/2 the electric field epsilon naught area times the distance, the separation between these two plates, right? But what is this? Look, area times the distance. Remember, we have these two capacitors. This is one capacitor, right? And this is the area 1, right? This is the area. We have another one right here, and that's the distance between these two plates. Now, if we multiply the area times the distance, we have the volume of the capacitor, right? The volume between these two plates. Perfect. So this is then equals to 1/2 electric field epsilon naught times volume. And then, well, we can define this energy density, right? Energy density, right, equals to energy per volume, correct? Energy per volume is equals to 1/2 or epsilon electric field epsilon naught divided by 2. Correct. So this is called the energy density, energy per unit volume. Okay, energy. Well, let me write right here. It's gonna be energy per volume is equals to epsilon naught E squared divided by 2. This quantity is very important in analysis for the speed of light in the next chapters. Okay, well, with this we finish this analysis for the capacitors, right? And thank you. See you in the next video.